Okay, thank you. So I'll just wait for a few minutes before starting. So, all right, let us start then. Okay. So, this week's materials are based on this Viterbi decoding and maximum entropy models. So you might have seen that there are a lot of materials in the lecture, but those are more for your knowledge. So we will only be covering the important topics like the ones you might be having questions in and so on. So let us start. All right. So the first question is kind of based on things we have already covered, but it's like a continuation of last exercise. So as you can see, so this is a question based on first order hidden Markov model, and you have been asked to calculate. So there are these three imaginary words you have been given, that is key, fin, and yeni, and there are these four pos tags t1, t2, t3, and t4. So as you can see, you have been given two tables. The first one is the emission matrix and the second one is the transition matrix. So based on these tables, you have to calculate the probability of the sequence they have asked. That is, x1 is key, x2 is fin, and x3 is yeni. Given y1 is t2, y2 is t3, and y3 is also t3. So x are the words over here and y are the post tags which you have to assign. So this is based on the simple Markov model theory. So what we need to do is that first we need to break down the entire probability sequence given into the conditional probabilities that we need. So firstly, you have to look at that like the y1, y2 and y3, these are the states, whereas x1, x2 and x3, these are the observables or the emissions. So when we start, so y1, probability of y1 being t2 into x1 being key, given that y1 is t2, then we multiply it with the transition from y1 being t2 to y2 being t3, and then you have to also multiply it with the probability that x2 we are emitting fin from y2 which is t3. And finally, the last part of the sequence is y3 equal to t3 given y2 equal to t3 and x3 is any. So this is quite simplistic. This is similar to the problems we did last week. And if you solve them out, then you get this answer, which is 6 into 10 to the power minus 5. So this is pretty straightforward. You just need to break down the entire probability sequence which has been given into the conditional probabilities. So remember, you have to form the chains. So how do you form the chains is that you need to transition from one tag to the other, and at each transition you need to find out the probability of the required emission. So that is how we get the chain. And because it has been mentioned that all post tags are equally likely at the start of the sequence, so that is why the first term, probability of y1 being t2, that one is 1 by 4. There are 4 tags, so 0.25, and the rest of the values you can get directly from the two tables, and that is how we come up with this answer. Alright, so this is more or less similar to whatever we have done the previous week. And a follow-up question along with it. So they have asked calculate probability of y equal to t3 given y1 is t4, y2 is t1, x1 is key and x2 is fin. So I would like to ask you to give an answer to this. So this is actually a one-word answer. You have to find out intelligently which ones, like the hint is that all the conditionals won't be applied, so you have to find out which conditional is actually applicable. So could anybody give a guess? So
I think the conditional is y3 equal to t3 given y2 equal to t1.
yes, you're absolutely right. So because this is a first order hidden Markov model, so that is why you need to remember two things. Firstly, when you are seeing that the first term on which, like whose probability you will calculate, if that is a y, means we are considering the states here. So any state will only depend on its previous state. That is the rule of first order Markov model, right? So automatically you can understand that y1 will not be considered. For y3 only y2 should be considered. And also you need to remember is that the states which over here are the y's, they do not depend on the emissions which are the x's. It's the other way around. Like xi depends on yi and nothing else, and yi depends on yi minus 1. These are the only two dependencies in a first order hidden Markov model. And that is why, even though there have been so many terms given on the conditional part, the only thing which y3 actually depends upon is y2. So yeah, this actually boils down to probability of y3 being t3 given that y2 is t1, which comes to 0.8. So yeah, right answer over there. um if you have any doubts regarding first order hidden Markov model, you can tell, because after this we'll be going into the entropy models. So this is kind of like continuation from the previous class only, I guess. uh, it's more or less clear. Just remember the two things. One is that a state only depends on its previous state. So yi depends on yi minus 1 only, nothing else. And the very first one, like y1, will not depend on anything, obviously. And the other thing to remember is the emissions, which are the x's. So xi will depend only on yi, not on xi minus 1, yi minus 1, nothing else. So these are the two things you have to remember for first order hidden Markov models. That is, yi depends on yi minus 1 and xi depends on yi. That is all. Every other thing has to be eliminated in the equations so that you can get the values directly from the two tables which you have. Like, these tables mean the same thing, right? So for example, key, fin and yen, so like this value 0.1, that is probability of key given t1. So xi equal to key given yi equal to t1. That is how you read the table. And on the other hand, the transition is like probability of yi being t1 given yi minus 1 is t1, that is 0.18, and so on. So that is how you read the table, and you have to break down anything which you have been asked to find out in that form. Then only you can use the values directly. So while breaking down, remember the two main things. Yi depends on yi minus 1 and xi depends on yi. Nothing else is dependent on each other. All the other things are independent.
So I have a question here.
Yeah.
May I ask?
Yeah, yeah, yeah.
So, in terms of the number of possibilities that we actually explore, right? In case of hidden states, we consider the possible values for each of the state for a given length of the string, right? So, does the observable sequence play any role in terms of arriving at the search space?
Um, Actually, I didn't get your question fully. But let me just rephrase everything once again, and then maybe it will be easier to understand. So you will be asked to. So for example, these problems you are asked to calculate a probability. So let's just go to the previous one. So you have been asked to calculate a probability where you have been given that find the probability that x1 is this, x2 is this, and so on. So when you have been asked to calculate a probability, it can be in this form of joint probabilities where everything is like comma, separated by commas. So like probability of all the things happening together. Or you can be given a conditional probability like the second question. So whatever you are given, you have to break that down into that form, like into a chain like form as we did over here. All right. So when you break it down into the chain form, then you have to remember the two golden rules, which is yi depends on yi minus 1 and xi depends on yi. Everything else you can separate out. So that is the main idea. Obviously, what how the chain will break down will depend on what probability you are being asked to calculate. So you are saying something about the sequence. So the sequence is also mentioned as part of the probability. So the sequence they are asking here is like key, fin, yeni, x1, x2, x3. So that is the probability you have to find out. Also given that y1 is t2, y2 is t3, and y3 is t3. So when you are given a probability to find out, you have to break it down in this format, right? So
Yeah, so the in this case, key, fin, any,
hmm,
the three words, three observables.
hmm.
Uh, in the worst case, right? Do we assume that key if in n, all three could be possible in the first position, and all three could be possible in the second position, and all three could be possible in the third position? Do we assume like that? Or since it is given that it is key if in n, we
Yeah.
always assume that the first position is key, and second
Oh,
position is pin, and third position is n?
yeah, like the that matrices which are defined, that can lead to any sequence of emissions. All right, but when you have to calculate what the sequence you are supposed to be calculating is given in the question, so then you don't need to assume anything anymore. So they are asking you explicitly to calculate the probability of the sequence key fin any, so you don't need to assume that something else will be in the first position. So that is what I was saying, what you have to calculate will be given to you. Now the if you just look at the two matrices, yeah, any combination of anything can be possible. So that is why they are asking to calculate the probability, right? Because some other sequence can also occur. Like, did that answer your question?
Yeah, thank you.
All right. Let's move on to the next question. So you have to, so this is a question which is based on maximum entropy. So you have to design a 17 sided dice, like consider an imaginary dice which has 17 sides. And they have asked that you have to design it such that the maximum entropy for the probability distribution of getting different sides on the same throw. So what does this mean is that for any dice there will be a probability distribution of what you get when you throw the dice. So for a normal dice with 6 faces, you have probability distribution being 1 by 6 for each of the 6 faces. But here they have asked you to design an imaginary dice such that the probability distribution yields the maximum entropy. But also there is a constraint, and the constraint is that the probability of getting 1, so you have 17 sides, so probability of getting 1 or like the side having 1 is 0.5. So this is a constraint which has been given to you. Now you have to design the probability distribution for the entire thing, and then what will be the maximum entropy. So this is the question. So this is like probability based questions. So how we do this is, so I guess you are familiar with the concept of random variables. So first of all, we have to take a random variable which represents the side when we throw the dice once. So let S be that random variable. Now you have been given in the question that probability of S equal to 1 is 0.5. Now you know that the sum of all the probabilities of all the sides will have to sum up to 1. That is like a universal probability rule. So you add up all the sides. So probability that we get 2 plus probability we get 3 and so on up to probability we get 17. That will be 1 minus 0.5, because this one has been given by the question that there is this constraint P1 equal to 0.5. So the sum of all the other p's from 2 to 17, that will be 0.5, 1 minus probability of S equal to 1. So this one you get. Now they have asked you to maximize entropy. As you know, like this is there in the slides, that the entropy is maximum when all the outcomes are equally likely. So when all outcomes are equally likely, then you have the maximum entropy. So we have to distribute the probability mass equally among all the sides. Now, if this constraint was not given, that P1 equal to 0.5, we would have distributed the probability, like the entire probability mass, which is 1, among all the 17 sides. So everyone would have had a probability of 1 by 17. But because this constraint is there, and we have actually seen that all the other ones sum up to 0.5, so that is why each one will be then 0.5 divided by 16. Why 16? Because one side has been taken care of previously already. So here we are considering the remaining sides. So all of them have to be equal to generate the highest entropy. So we have to distribute the mass evenly between all of them. So 0.5 by 16. Okay, so that is 1 by 32. Now you have got the probability of every side. So probability of s equal to 1 is 0.5 and probability of all the other faces is 1 by 32. And then this is a simple formula for entropy. So you have one side which is having this probability half. So minus half into log of half. And then you have 16 sides which have probability 1 by 32. So minus 16 into 1 by 32 into log of 1 by 32. So if you solve this thing, it will come to 0.5 plus 2.5, which is 3. So this is a very simplistic problem. The only trick in this problem was that you have to find out the max, like you have to design it for maximum entropy, and that is why we have to distribute the probability mass equally. That is the only trick in this problem. Alright. So do you have any doubts regarding this particular problem? Alright, I guess not. So let's go to the next one. Now this is going to be a bit difficult, and so let's walk through it slowly. Even in the slides this has not been elaborated very clearly, so this will be an important example. So this is about beam search. So you have heard about beam search definitely. So now, and this is on a maximum entropy Markov model. So as you know, in these maximum entropy models we can assign features. Now you might be getting confused that what are these features exactly. So feature, you can consider a feature as a function of a given observable and hidden state. So feature is like a function of x and y, and the feature, that function returns a value of 0 or 1, basically whether that feature is applicable or not. For example, here you have been given the list of features to consider. So there are a possible of 4 tags, T1, T2, T3 and T4, and these are the possible features. So for example, this feature F1, this is saying that T1 equal to T1, Ti equal to T1 and Ti minus 1 equal to T1 or T2. So for any given X and Y or word and tag, so here there is not X and Y, here there is W and T. So W represents the observables or the words, and T represents the states of the tags, right? So every feature over here is a function of like W and T, and the condition is given. So for a given W and given T, if a feature like if the conditions for a feature holds, then that feature will return 1, else it will return 0. That is what these features mean. Alright, so you have been asked to like assign pos tags to the sequence key fin ene using maximum entropy Markov model with beam search, where the beam size will be 2 and all the features have weight 1. So you have to find what will be the tags of the sequence key fin ene based on these features. Alright, so before we go into this, let's have a look at the slide which you have. So this is the formula which is important over here, right? So at every, you have to calculate for every word and every tag. So this is how you have to do these problems. You have to calculate like the possible values for every word and every tag. Now when you look at the equation over here, it can be intimidating, so we will walk through them slowly. So if you look over here, so just look at this part, summation over I lambda I fi xy. So I represents all the features over here. So for a given x and a given y, you calculate the numerator as e to the power sum over all features. So how do you sum over the features? As I said, each feature represents a function which returns 0 or 1, right? And lambda I is the weight of every feature. Now in the given question, you have it has been mentioned that the weight of all the features are 1. So you can think that in the equations we will use this lambda I won't be there because all of them are 1. So you have to sum up all the features for a given x and y. That is the trick in the numerator. And in the denominator, you have to sum that up again over all y's. So how does this play out actually? Let's look. Okay. So in the question you have been said that there is some allowed post tags. Now, technically, if there was no constraint, it would have been possible that all tags can be applicable for all words. In that case, you would have had to do a lot more calculations. But because the constraints are given, you don't need to consider some combinations. Like, for example, they have said that for key, the post tags allowed are T1 and T2. So you don't need to consider the combination of key with T3, T4. Similarly, you don't need to consider combination of fin with T1 and so on. So you just need to look at the combinations which are allowed, right? So how do we do this? So the first word is key, right? First word is key, and the first tag, like the possible tags are T1 and T2. So you have to calculate the value which I said before, which is this one. So you have to calculate this first for T1 and then for T2. The denominator will be common for both. Alright, because the x is same over here, which is key. So again, let me be clear. In our case, the x, like the step we are doing right now, x is the word key, and the possible y's are like, in this case, y is T1 and T2 only we have to consider, right? So yeah, now if you look, how do we do that? So look at the combination of key with T1. So Wi is key and Ti is T1. Now you have to look how many features are applicable for the numerator part. Let's forget about the denominator for now. Just look at the numerator part. Alright. So if you look at the numerator, what are the possible things which we can have? So for T1 and key, is there any feature which is applicable? So if you look, so because the lambdas are all 1 in our case, so that is why you just need to count how many features are applicable for a given combination, and that will simply be the value which appears at like the power of exponent. If the lambda values were given, like say lambda 1 is something, lambda 2 is something, and so on, then you would have to weight them accordingly. But because the lambdas are all 1, you can just simply count how many features are applicable, and then you can just add it up over here, right? So for key and T1, so T1 is like, Ti is T1 and Wi is key. Can you find any feature which is applicable?
So
So
I have a question. In the feature one, we do not have the role of W1, right? It is
yeah,
solely dependent on Y's.
yeah, like
Is it
all,
okay?
huh?
Is it okay? Should we consider that feature in this case, in case of key and T1?
So when the Wi is not part of the feature, that means it does not matter what the word is. Only you need to consider which tag we are in right now, right? Okay. So like there are two features, like there are three features like that where you do not have the W's. So it only depends on what is the current tag and what was the previous tag. So we are at the tag we are considering currently is T1. So there is only one feature which is considering Ti equal to T1. Okay. So Ti equal to T1 and Ti minus 1 is T1 or T2. Now in this case there is no ti minus 1. This is the very first tag, right? So that is why this feature is not applicable. F1 is not applicable, F2 is not applicable, F3 is also not applicable, and all the other ones, they are obviously not applicable because the wi is key. So for the word key and the tag t1, there is no feature which is applicable. So we have e to the power 0. We'll look at the denominator later. Now consider the word key and the tag being t2. How many features are applicable? This one. So the current tag is t2 and the previous tag is null. So this feature is applicable, right? F2. So that is why you have e to the power 1. All the other features are not applicable if you have a look closely. Fine. So that means that for t2 there is only one feature applicable, so e to the power 1. And then in the denominator is for normalizing. So if you calculate all possible combinations, then the denominator will be like the sum of all the numerators. So e0 by e0 plus e1. So you have e0 and e1 as the possible numerators, right? So the denominator will be e0 plus e1. e0 plus e1. Now that is a very simple heuristic, but if you look at the formula, the exact same thing will come, because it is saying that in the denominator we have to do sum over all possible tags. Numerator is combination of given word and given tag, whereas denominator is given word with all possible tags. So obviously, because we are calculating the numerators for all possible tags, the denominator is just for normalization. You have seen that also, like they are mentioning that the denominator is a normalizing constant. So that is why we get these two values. So this is the very first step, and we get the values as 1 by 1 plus e and e by 1 plus e. Fine. I've given them different colors to denote, like we will be needing them in the next stages. Now for key, they have said that there are only two possible tags which are there, and so we have two possible values. They have said that the beam size is 2. So beam size means at every point we have to consider the two highest values. In this case we only have two values. Suppose there was another one t3, suppose, then there would have been three values, and we would have chosen just the two maximum values to carry forward to the next step. Okay, so what is this next step? Let's go to it, then we will be clear. Now the second word is fin, and the possible tags are t2, t3 and t4. All right, so let us look at this thing, and we have to remember one thing, as in where are we coming from. So as the beam size is 2, in the previous step we have two maximum values, right? And you have to consider the combinations at the current step with all possible values from the previous step. Because the beam size is 2, you only need to consider combinations with the two highest values. All right, and you have to remember where they came from. That is why I have used the colors. So the red is for t1, like coming from t1. Like, why we need to remember that? Because you see there are many conditions where you have, which are like the features are conditioned based on the previous tag. So we need to keep a track of which tag we have seen before this, right? So this red color is for t1, and this pink purple kind of color is for t2. Okay, now let's see how this is happening. So we have t2. So let's consider the first case. Current tag is t2, current word is fin. All right, and when we are considering the first one, previous tag was t1. So previous tag t1, current tag t2, current word fin. What are the features which are applicable? Are there any features like that? Probably not. There is no feature. which is applicable for this combination. Remember, because this is the second step, you have to consider what the tag was in the previous step. Alright, so current tag T2, previous tag T1. There is no condition like that.
F1 is there, no?
No, F1 is current tag being T1. We are considering current tag T2.
Oh, okay, okay.
Alright, so that is why we have e to the power 0 over here. Why 3 as denominator? You will see when you do the normalization. So leave the denominators first, just do the numerators, and then you just sum up the different numerators to get the common denominator. Alright, so this is this case. Now let us have a look at the next case, which is current tag T2, previous tag T2, current word fin. Are there any features which are applicable for this combination? Again, no feature is applicable. So that is why we have e to the power 0. So I am just discussing right now this part which is in white for all the different conditions. The colored parts, they come from the previous step. Like you have to multiply the probabilities. So this part, it has come from the previous step. So this one is again E0. We'll have a look at the denominator later. Alright. So this is E0. Now let us look at current tag T3, previous tag T1, current word fin. Again, there is no possible feature for this combination. So again we have e to the power 0. Then let us look at current tag T3, previous tag T1, previous tag T2, and current word fin. So one feature is applicable, right? Which is that one? That is
First one. Current, it's not first one. Third one.
yeah. Current tag T3, previous tag T2. This one is applicable. So e to the power 1. Fine. Then we have to look at current tag T4, previous tag T1, current word fin. No feature is applicable. So 0. Finally, current tag T4, previous tag T2, current word fin. So we have that one, this one. F3 is applicable. So previous tag is T2 and current tag is T4. So this one is applicable. Also F6 is also applicable. Current word fin, current tag T4, previous tag T2. So we have two features which are applicable when for this combination, this one. So we have e to the power 2. Right. Now remember that each line represents a conditional, right? So this one, and this one, the numerators, some of the numerators will be the denominator, like the first lines of every combination. So we have e to the power 0, e to the power 0, e to the power 0. So 1 plus 1 plus 1, that is why the denominator is 3 for this case. 3, 3, 3. But
Can you please explain why we have to divide them into two sets?
huh?
Why we have to consider only one of the rows for normalizing?
Because each row represents this possible combination also based on what was the previous tag. So when you normalize, so like all the conditionals have to be same for normalizing. So why we are not considering these numerators as part of the entire thing? Because in these cases the previous tag is different, right? So you have to consider, like for normalizing, you have to consider only those rows or combinations which have the same conditions. All
No,
right.
if you go to the formula, you said that sigma has to be done over all y's, right? For the normalizing thing.
Yes, all y's as in yi, not yi minus 1. Like there may be two different yi minus 1s, so you have to
Correct.
consider them differently.
So if you consider yi,
Ha.
that means you have to consider the current tags only, right? So if the current tag is T2, then should you not normalize on the both of the rows for each thing?
No, no, no. That is, let me go over it once more. When you normalize, then what are we normalizing over? So the word is same, like current word is same for all, right? Wi is same for all, and the ti minus 1 also has to be same. We will normalize over those combinations which have the same ti minus 1 and same wi. All ti's, like sum over all ti given same wi and same ti minus 1, like t and y interchangeably. Okay, like in the formula it was y, but in the question it's t, right? So, like, did you get it?
Yeah, yeah, correct. So my question is, like, in the formula it is in y, it is y. So
Hmm.
we are normalizing over all possible t's, right?
All possible t's of the current state, given that
Correct.
if the previous state t's are different, then you can't consider them together for normalizing.
Okay, okay, all
So
right.
that is why the first rows have the same ti minus 1, we will normalize over them. The second rows have the same ti minus 1, so those will be then normalized. You have to do them separately, right? So
Okay,
remember, when you normalize, you have to normalize over all possible values of ti given the same wi and same ti minus 1.
all right. Okay.
So then that is straightforward. For the second part, we have e to the power 0, e to the power 1 and e to the power 2 as the three numerators. So that is why the denominator is 1 plus e square. Alright. And then you just need to multiply it with what you came from. And then you will have 6 different values. Like like why these problems become a bit difficult to keep track of is because they start to explode. At each point you have to consider so many combinations, right? So that is why, to make your job easier, the tags are usually restricted so that you don't have to deal with exploding combinations. But ideally, had these constraints not been there, then there would have been even larger number of combinations to consider. Also, if the beam size was larger, say if beam size was 3, then we would have to consider 3 rows per tag. Like, you are getting how it's working out, right? I can understand that this particular type of problem, just by going over it once, it might not be fully clear. So I'm trying to explain the same things as many times possible, but maybe you will again have to go through the problem and look over it to get a completely clear understanding. Okay, so remember, when we do the normalization part, we have to consider normalizing over the same wi and same ti minus 1. All right, so that is why the first 3 rows, they are part of the same normalization, like this row and this row, and whereas the second ones are part of the other normalization. That is what you need to remember. And we get all these possible values. Now they have been, like, you have to go with beam size 2, right? So we have to take the two largest possible values. So if you actually calculate, the largest possible values are these two, this green and the blue one. E square by 1 plus e square into 1 plus e, and e cube by the same thing. Like, these are the two largest values, this green one and the blue one. Like, when you consider which values to choose, then you have to look among all 6. Once you get these values, then you need to forget where you came from and everything else. You just take directly the two highest values. All right, so the two highest values here are this green and this blue. Now let's go ahead and complete it, then you will understand how it's all adding up. Finally, this is the last word, which is yenny, and the possible tags are T1 and T4. All right, and where have we come from? This green and blue. What is green and what is blue? So green means the previous tag was like T3. Green means previous tag is T3. Blue means previous tag is T4. So now we have to look at the possible things for T1 and T4. Alright, so again we repeat the same thing. Current tag T1, previous tag T3, and current word any. How many features are applicable? So one feature is applicable, which is this one,
F4, F.
F4, right? So F4 is applicable. Current word any, current tag T1, previous tag T3. So e to the power 1. And if the previous tag was actually T4, then nothing is applicable, because current tag is T1, previous tag T4, current word any, nothing is applicable. So e to the power 0. Same way we go for T4, current tag T4, previous tag T3, and current word any, no feature. Current word T4, previous tag T4, current word any. This one, F5. You can see F5. Current word any, current tag T4, previous tag T4. That one is applicable. So e to the power 1. Again, when we normalize, these two are coming from the same previous tag, which is T3. So we need to consider these two together. So 1 plus E, and also these two together. So 1 plus E. So new denominators in both cases 1 plus E, but you need to remember how they are coming. This one is coming from e to the power 1 plus e to the power 0. And this one is coming from e to the power 0 plus e to the power 1. Like those two are separate. Here the final values are same, but it was different over here. So I guess that part is clear. And finally you multiply with whatever you came from. And then we have all these possible values. And we can see this is the largest because the denominators are same in all cases. This one has the highest numerator. So then we end up with, so this is the final probability of the entire sequence, like the highest probability. And what is the path we have taken to reach here? So at the end we have T4. We have come from T4, and that blue T4 came from T2, right? So the optimal path then is T2, T4, T4. And before I take questions, for this, let me just cover the next question, which is this same problem. They have asked to calculate the probability, which we have already got over here. You just need to find out the value. That's all. Which comes to this. All right. So question 4 and question 5 were linked. Here previous one was asked to find out the optimal sequence, and this one is the optimal probability value. All right. So I'll just go over this once more in case it is a bit difficult to understand. So somebody had a question. How to select the allowed post tags? Oh, that is, you don't have to select that. That will be given in the question. If it is not given in the question, like here they have said allowed post tags are this. If that is not given in the question, then you have to consider all possible tags at all possible steps. Like in our calculation, we have considered for key only T1 and T2. We are not considering T3, T4. For fin, we are not considering T1. For Yeni, we are not considering T2, T3. If this part was not given, allowed post tags, so on, then you would have to calculate all 4 combinations for all steps. Alright. So I'll just walk through this one once more, but you will still have to look at it later to get the full understanding. What you need to do is, over here you need to count the features, because the lambda or the weights of every feature has been mentioned 1. That is why simple counting will give the final value over here, like at the numerator, like e to the power whatever, that will be given by simply counting the features. Had there been weights given, then you would have had to multiply those weights based on which feature is applicable and so on, like making the problem even more complicated. So if you just remove the lambda part, which are the weights, you just need to count how many features are applicable for the given combination. What is the given combination? At any point you are considering one particular word, which is wi, which has been given. You have to find this sequence, so you know what is w1, w2, w3, you know that. And you have to consider all possible tags, like ti combinations have to be considered based on what is allowed. And finally you also have to remember what was the previous tag. Now these are multiple branches of calculations and they have to be maintained simultaneously. Why? Because beam size is 2. If beam size was 1, at every step we would have taken the maximum and continued ahead with it. But because beam size is 2, the calculations will branch out, right? There will be possible branches and you need to keep track of that. That is all this is about. So you need to calculate the number of features which are applicable for the given combination of wi, ti and ti minus 1. For the first word there is no ti minus 1. Basically ti minus 1 is null. Alright. So that is there. And in the next steps you also have to consider the ti minus 1. This is one part of the main trick of this problem. The second part is how to calculate the denominator. So the denominator is for normalization. First you find out all the numerators and then you sum up all the numerators that have the same wi and same ti minus 1. This is very important. The ti minus 1 has to be same, then only you can normalize over them. You cannot consider all possible ti minus 1s for normalizing. So all the values which have the same ti minus 1 and same wi, we normalize over all values of possible ti's. That is what the normalization means. So if you, again, most problems in this course are like this. The calculations are not complex, but you have to remember the steps very mechanically, like you have to do it in a mechanical way. And that makes sense because people previously used these models for calculation and all. So this is like an algorithm. You have to follow the algorithm and you will get the answer. So remember, for these problems what you need to take care of are, when you are counting the features, you are looking at a given combination of ti, wi and ti minus 1. When you normalize, you will normalize over everything that has the same wi and same ti minus 1. And then you just multiply and calculate values. At each point you choose the highest number of, like, n highest values, where n is the beam size. Here beam size is 2, so at every point we are taking the two largest values. And finally we multiply them, we keep on multiplying with the previous step. You have to keep a track of where you came from so that you can apply the features in a proper way. That is why the denominators are different, or like the numerators are also different for the two possible paths, based on whether we have come from t1 or we have come from t2. All right. And when you get to the end, there you find out the highest possible value, and from there you go back to find out which was the actual path we came from. That is why over here I have used the different colors for understanding. So at the end we found out this as the highest value, this came from this, and this came from this. So that is how we are going to this. All right. Okay then. I hope this is a bit clear. I can understand that it might not be 100% clear to all of you, but I am hopeful that if you go over this lecture once again, if needed, then it will be clear. Just have to remember the simple steps.
Shounak, I have another question, general question.
Yeah.
In the assignment 4, there were some problems about general Markov chains.
Okay.
Like in terms of how to calculate probabilities and how to come up with expectations, etc. Will it be possible? Have you already conducted a session? Because last week I did not attend. Have you already conducted any session about solving such problems?
Yeah, last week I actually covered some problems based on Markov chains only, but they were first order Markov models. So yeah, like even the first problem, like problem one, question one and two in this slide is also kind of based on similar things. So yeah,
So
that has
okay,
been.
so in a Markov chain, like it in the assignment, it was I can describe the problem. There is a seven-step or eight-step process,
Hmm,
eight-state process.
hmm,
So some probability was asked to calculate. Of course, that is straightforward.
hmm.
How do we come up with expectations around the possible states, which will maybe in the fourth stage or fifth stage or something like that?
Okay, so in particular, I did not cover expectation as it is. So because today I have limited time, I can probably address this question in the next class. Okay.
Okay, all right.
So I'll just keep a note of it. So even if I'm not able to, okay, I'll try to cover it in the next class. So you're talking
Next
about
class is
expect,
next week, is it?
huh?
Next class is it next
Yeah,
week
yeah,
or
next,
before the
yes.
submission date?
Uh, like
Our submission date is tomorrow.
okay, then you just send me a mail and I'll try to look into it. Then you send me a mail. All right.
Okay, okay. Will you share your email address, please?
I'm sharing it right now. I hope you have got it. So,
Yes, I got it. Thank you.
so I can understand today's session is a bit tricky. If you have any follow-up questions, you can ask me in the mail. But I have to leave now because I have some other engagements. So I hope that's okay. And all right, thank you everyone. If you have any doubts, critical doubts, you can ask me in mail. All right.
Thank you. Thank you very much.
Yeah. Thanks.
So whether the slide will be shared to us
Yes. Yes. Yes.
when, sir? Uh, at least by today?
Yeah.
Is that possible?
Yeah. Bye today.
Okay.
Sure. Thanks.